two types of microscopy. One is side scattering microscopy, and other one is confocal microscopy. Confocal microscopy comes from the top to bottom. So the problem is laser coming here. So this is bright. As laser penetrates to a solid substance or specimen, the light is somehow attenuated and somehow scattered. So that's why on the top it is black. This is the problematic region. How to overcome this problematic region? So most of the information lost because it is dark, and this one is clear. For example, this is a real image. It is a Drosophila and embryo. Drosophila is kind of very common biological species. And say for example embryo, and it is the egg. So this side bright and here is black. So how to overcome this situation? This is my motivation. Normally, the general people attack this problem from the point of convolution. Convolution is the opposite process of opposite process. Therefore, when it passes through a pinhole camera, I will explain later. This is the mathematical convolution operation. Say for example, this is the offset, and this is the transfer function, that is the media, and it comes to the noise, and finally it is the observed image. So this is the original image and this is the observed image. So how we can find the observed image? Observed image is equal to convolution operation of transfer function, that is the media, through the media, either optical media, either any other media, plus noise. And this is the approach, conventional or traditional approach scientists are normally doing in this order. And I'm giving you what is the pinhole effect. Pinhole, the light passing through a very narrow path. Here is the microscope. So object and sample is here. And I'm showing, for example, just a focal plane. Find the focal plane through a pinhole. It's just focal plane. When it is out of focus, that is 1 micrometer from the focal plane, and there is some interference. But it is our desire. So more further from the focus, it is more interference. This is the out of focus problem. Normally people use the deconvolution method, and because the image formation through the convolution method, so they do the opposite process, which is called deconvolution, inverse of convolution. And here we are attacking this problem through physics-based method or physical model. Physical model, I think, is the undeniable truth. We formulate a mathematical formulation how when the light comes, it incident on a particle, and this particle some light absorbed, that is attenuated, and then the less amount of light passing from particle to particle. But when a particle absorbs some light, it is the property of light, it has scattered that light. And this mechanism mathematically we formulated. Say for example, here is the dust. How, say, for example, the less amount of light, few photons coming through, and most of it scattered and attenuated. Here is more few. And attenuation and scattering phenomena, I am not talking about the details of the mathematics, but anyway, here is our final intensity. This is the object, and final intensity equation is like this. If you consider only the attenuation component, not consider the scattering component. Scattering component contribution to the total image formation is lower than attenuation, and attenuation is normally exponential. But this physical model, some scientists make physical model for other types of applications. At the first image, I show a foggy image. Foggy image is media is removed. But for microscope, media, that is fluorescent media contains information, so we cannot exclude the media. Or underwater, here is also media removed. Underwater image formation, the media is removed. But our microscopy is completely different from the other types of physical approach. And the algorithm, our target is the minimization problem. How to find the rho. Rho is the intensity, that is the light intensity. To find the light intensity, normally we can use genetic algorithm or other types of gradient or differentiation gradient technique. But here we use golden section minimization to find the exact. Golden section minimization is used in such situations where it is tedious or it is difficult to find the exact differential gradient or exact gradient. So this is a simulation image, and say for example here the brightness bar, and like a model, we made the synthetic image into a model of microscopy image. So after my processing or my application of our model, just use homogeneous light. So this part light, homogeneous.